Okay, so notes 5 is over discrete and continuous random variables. You will need some highlighters if you don't have them out already. So it says a random variable takes numerical values that describe the outcomes of some chance process. So very important, when we're talking about random variables, we're talking about numerical values, not categorical values. Okay? Random variables involve the same probability rules. So the ones that we learned in the first half of the unit, we're still using all those same formulas, but we're going to extend them to be able to use them for more events. So let's think back to our example when we talked about what would happen if we toss a coin 3 times. So first we talked about what the sample space would look like. And that is all the different possibilities if we were to flip those 3 coins. So we could have tails, 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 heads, tails, heads, tails, heads, tails, tails. Which one did you say? Heads, tails, heads. Good. Heads, heads, heads. We're missing 2 more. Yep, tails, heads, head. We got that one. Heads, tails, tails.
Head, tails.
Tails, tails, head.
Head, head, tails. I think that was it. Head, head, tails. Yeah.
Yes, I got it.
Okay. So that is our sample space. So what that means are those are all the different possibilities we could get if we were to flip the coin 3 times. So what is the total number of outcomes?
6, 7, 9, 8.
8. Good job. Okay, what's the probability of one outcome happening? 1 out of 8. So this example here is what we did when we talked about probability. Okay. Now let's say instead of using our terms for probability, we transform this into random variables. How that would look like is we actually assign a variable x to represent something. So in this case, it says let x be the number of heads out of 3 coin tosses. So what does it mean if x is 0? There's no heads. What does it mean when x is 1? There's 1 head. What about when x is 2? 2 heads. And what about when x is 3? 3 heads. Okay. And we know the probability of each of those by looking at our sample space. So how many times do no heads appear? 1. So that's 1 out of 8. Okay. How many times do 1 head appear? Only 1. 3 out of 8. What about 2? 3 out of 8. Okay. And then what about all 3 are heads? 1 out of 8. And if I was to add all these together, what should I get? 8 out of 8, which is 1. I should get 1. Remember, the total probabilities add to 1. Bless you. Okay. Then it says, with these 4 x values and their corresponding probabilities, we can create a frequency table and a histogram. So each of these, we had x assigned to 0 to 3, and then we found the following probabilities. We found that 0 is 1/8, 1 is 3/8, 2 is 3/8, and 3 is 1/8. Okay? So if we were to plot this in a histogram, remember, histograms have bins that touch or don't touch? Touch, right? If they don't touch, what is that called? A bar graph. So they do touch. So from 0 to 1, we know that is 1/8. From 1 to 2 is 3/8. Okay. For x equal to 2 is also 3/8. And for x equal to 3, that is 1/8. Okay, notice that all our bars or our bins, remember we call them bins, are touching. And of course, this would all be colored in. Okay. The frequency table and the histogram represent a probability distribution. Okay, so we're talking about new types of distributions now. What was the very first one we learned about? The standard distribution. Good. And within the standard distribution, we talked about what type of curve? The normal curve. So within the probability distribution, we're going to talk about what is called the density curve. And we'll talk a little bit about that at the end. So it says a probability distribution tells us the value that our random variable can take and the probability associated with each value. Okay. So now let's talk about some requirements in order to have a probability distribution. It says there is a numerical random variable x. And each of the values of x has an associated probability with it. So notice it says numerical, and then in parentheses it says not categorical. Okay? This means that all of our random variables have to be assigned a number value. We can't say our random variable x is equal to all types of dogs. Okay? It would have to be a numerical value. The sum of all the probabilities in the distribution can be written as the summation of the probability of x, and that must be equal to what? 1. Remember, all our types of probabilities, when we add them together for each event, would equal 1 or 100%. Which tells us that each individual probability within the probability distribution has to be between 0 and 1. Okay, makes sense because if we were to add up all the individual probabilities, okay, we know it has to equal 1. So our individual ones, just like from the coin toss one, they were all less than 1. 1/8, 3/8, etc. are all smaller than 1. Okay. Now let's talk about the notation. Okay. So instead of saying probability of this, and it was written in sentences for the probability examples, now we're going to have it written in an equation. So for example, if we see probability that x is equal to 2, that is the same thing as asking what is the probability that the random variable equals 2. So go ahead and highlight that. The random variable equals 2. So I would go off to my frequency table, I would find 2, and I find that my probability is what? 3/8. Okay, then I look at probability x greater than or equal to 2. That's the same as saying what is the probability that the random variable is greater than or equal to 2. So since it has equal to 2, am I including 2? Yes, and then I'm including all the numbers bigger. So that's going to be 2 and 3. And what do you think I'm going to do with those probabilities? Add them. So 3/8 plus 1/8 gives us 4/8, which is 1/2. Perfect. So the probability that x is greater than or equal to 2 is 1/2. Okay. Then I look at probability that x is less than 1. That is the probability that the random variable is less than 1. So am I going to include the number 1? Why not? Because it's not equal to, so that means I'm only going to look at the values less than 1. In this case, that is when x is 0, and what is that probability? 1/8. Now we're going to talk about the two different types of random variables. So we have discrete and continuous. Okay. It says a discrete random variable takes on a fixed set of possible values with whole number outcomes. Okay, when you see the word discrete, I want you to think of a counting number. So a number that you count. So 1, 2, 3, 4, etc. Okay, random variables usually use capital letters. So the most common ones you're going to see are X, Y, and Z, but it can be any letter capitalized. Random variables must be numerical. Okay, so in our example, it says even though the result of heads or tails is categorical, we describe it numerically, and that's when we assigned X equal to the number of heads. So now we're not just saying heads or tails as our results, we're saying, okay, there was 2 heads when we did this, there was 3, etc. The mean of the discrete random variable X is the mean outcome for infinitely many trials. This is very important. This is typically one of those multiple choice questions. Okay, and they'll ask you what's the interpretation of the mean of a discrete random variable, and you're going to have to say that it is the mean outcome for infinitely many trials. Okay, what that means is if we were to do this same experiment over and over and over again, infinitely many times, we would expect that mean value to be whatever it is once we calculate it. Okay, so it says we think of this as the expected value because it's the average value we would expect to get if the trials could continue indefinitely. Do not confuse this with what we expect to get in a single trial. So if we were to all do the coin toss experiment in class right now and calculate the mean from that, that would only be what we would expect from a single trial because we did it one time with the 20 plus students in this class. Okay? Versus if I was to do this, let's say with every single class in this school, and then every single class did this from 9 a.m. till 4:20, okay? Then I would take the mean of that entire experiment. It would be closer to the expected value because we'd be closer to that infinitely many trials. Okay. To find the mean, which we're going to denote as mu x, or another name for the mean is expected value, which we denote as capital E of x, of a discrete random variable, we multiply each possible value by its probability, then add up all the products. So what that means is, let's say I have my table here, and I have x1, x2, ... xn. Okay? These are all my possible x values. And then on the probabilities, these are all the probabilities that correspond to it. So P1, P2, all the way to Pn. In order to find mu sub x, we take the x value and multiply it by the probability. So it would be x1 times P1 plus x2 times P2 plus all the way until we get xn Pn. Okay, so if we have 5 x values here, then it's going to be x1, p1, all the way till x5, p5. Okay, that's what that x sub n, p sub n represent. How many total possible outcomes are in our trial? Well, we can actually write this in terms of a formula, and this formula is how you're going to view it on your formula chart. And that is that mu of x is equal to our expected value, which is equal to the summation of xi pi. So again, this means this. Okay, the summation of xi pi is the same as saying x1 p1 plus x2 p2, etc. Okay, so for now in these notes, we are going to do all our calculations by hand. So we get used to the concept, right? And then I'm going to show you how to do this on Desmos on a different time. Okay? But just know all our examples are going to be very small x values, right? So it's not like I'm going to have you compute 100 plus x values in order to calculate the distribution. Okay, so example 1 says Northwestern University posts the grade distribution for its courses online. Students in Statistics 101 in a recent semester received 20%, 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. It says create a probability distribution for the random variable X, which represents the student grades on a 4-point scale with A equal to 4. So when it says create a probability distribution, I want you to think create a table. Okay, so go ahead and highlight that and write table. Okay, which means we're creating the table of X, P of X. Okay. And the number that we start with doesn't really matter here. So we can start with X is equal to 0, or we can start with X equal to, what does it tell us to say? Where A is equal to 4. Okay. I like to go in numerical order, so I'll start with 0 and go to 4. But again, the order doesn't matter as long as you're being consistent. So you can either be increasing your X values or decreasing your X values. So if I start when X is equal to 0, this is representing all the F's. Okay? So for the sake of the notes, I'm going to write what this represents. You would not be writing the parentheses F on your actual answer, right? This is just for the notes. So then I go up to F's, bless you, and then I look, okay, what percent were F's? 2%. How do I convert that to a decimal? Not 0.02. So this is 0.02. And then I look when X is equal to 1. Well, when X is equal to 1, that's going to represent what letter? D. Okay, and what percent or what probability was D? 0.10. Good. And then I continue this all the way until I get to 4, because 4 is representing our A. So X equals 2 is representing C. And what is the decimal for C? 0.2. Okay, then when X is equal to 3, this is when our letter grade is B. So what's our probability? 0.42. Good. And then lastly, 4, when our X value is representing A, what's the probability? 0.26. Perfect. So again, this is representing B. This is representing A. Okay. So when they're asking you to create a probability distribution, typically the information is given to you. You just need to convert it into a decimal for probability. Okay. The reason I like to do it this way is because it helps me answer the next couple questions, okay, because it's already in numerical order. So that would be my answer for A, okay. B says, find and interpret probability of X greater than or equal to 3 if X represents a randomly selected Statistics 101 student. So it says find and interpret. So I'm doing math and what? Which means write a sentence. Write a sentence. Okay, I just need to hear it from y'all because some of you still in the FRQs are not interpreting correctly. Okay, so if it says interpret, we write a sentence. We write a sentence. So first, let's find the probability of, I'm change the color, hang on. Probability of X greater than or equal to 3. So which X values is that going to represent? What are the X values greater than or equal to 3? 3 and 4. These values here, 3 and 4, because it's greater than or equal to 3. Well, we can write this as the probability of X equals 3 plus the probability of X equals 4. Okay, because that's ultimately what we're doing. We're adding those probabilities together. So that is 0.42 plus 0.26, which gives us 0.68. That is our find. So what does that mean? What is 0.68 representing? Say that one more time. 68% of students what? Good. Got a B or higher, right? So we would say 68% of Stats 101 students, okay, got a grade of B or higher. Okay, then part C says write the event, and here's the event. The student got a grade worse than C in terms of values of the random variable, and then answer the probability. So we're putting it in terms of the probability notation, and then we're solving. So what does it mean if it says the student got a grade worse than C? Did they get a C?
No, they got worse.
They got worse than C. So how would we write that? Probability that X less than 2. Good. There's another way we could write that. Probability that X, there's two ways to represent this. Less than or equal to 1. Those are the same thing. If we're less than equal to 1, then we're 1 and 0, right? If we're less than 2, we're still 1 and 0. So these are two ways, which means if you write either of them, you get the point. Okay. So let's say I just use this one, probability of X less than 2. That's the same as saying the probability of X equals 1 plus the probability of X equals 0. Well, that is equal to 0.10 plus 0.02, which is equal to 0.12 or 0.12. Which means 12% of Stats 101 students got a grade worse than a C. Not too bad. Okay. Then it says compute the mean of the random variable X and then interpret it. So we're computing, which means we're doing what? We're doing some math, right? And then interpret, which means we're writing a sentence. So first we have to recall, okay, well, what is the formula for mean? So mu of X, which is equal to the expected value of X, is equal to the summation of look back at the formula, X sub I and P sub I, which means we take all of our X values and multiply by their probability and then add them all together. Okay, so this is 0 times 0.02, that's when X is equal to 0, plus 1 times 0.10, plus 2 times 0.20. Okay, so I'm at X equals 2, plus 3 times 0.42, plus 4 times 0.26, which is going to give me 2.8. So that is my computation. That's the math part. Then it says interpret this value in context. So what does 2.8 mean? What does expected value mean? Remember, go back to expected value. That we expect if we did this trial infinitely many times. So we would say if infinitely many students took this Stats 101 course, we would expect their average grade of 2.8, or what does 2.8 represent in letter grades? Between C and B. Good. If infinitely many students took this Stats 101 course, we would expect their average grade of 2.8 or between a C and a B. You will always answer the interpretation part exactly like this. You're always going to say, if infinitely many blank, whatever the context is, we would expect their average blank, whatever the context is. Okay? These are the most important. If infinitely many blah, 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 we would expect their average to be blah, 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 depending on the context of the problem. Yes, question. How do we know what? Yep, C. We know because right here, 2.8 is between 2 and 3. So, and that's also representing C and B. That's how I know it's between C and B. Okay. Okay, next part, standard deviation. So remember when we talked about standard deviation in the beginning? Okay, we're going to come back to it for random variable. It says the standard deviation of a random variable is a measure of how much the value of the variable typically varies from the expected value. Every time you're asked to interpret standard deviation, you need to include those words. Typically varies from the expected value. These are the most important. Typically varies from the expected value. Okay. So if we were, again, using our table, x would be x1, x2, all the way to xn. And then p of x would be p1, p2, all the way to pn. So in order to find standard deviation, remember we have to find variance first, because standard deviation is the square root of variance. So in order to find variance, what we're going to do is we're going to take each of our x values, subtract our expected value, square it, and then multiply by the probability. And we're going to do that for every single x value. So it looks like x1 minus mu x squared times p1 plus x2 minus mu x squared p2 all the way to xn minus mu x squared pn. Okay. Or in other words, the variance equation, which is the summation of xi minus mu x squared times pi. Remember, this is just a way to expand the summation formula. Okay. And then once we find variance, we know that variance is the standard deviation is the square root of variance, which means we take the square root of the summation of x sub I minus mu x squared p sub I, the entire thing. So if we go back and we use that same example that we did, the Northwestern example above, it says find and interpret the standard deviation of the grade probability distribution. So we're going to use our same values from the table above, and we're first going to find sigma x squared, variance, right? So for variance, we're going to start with our x equals 0. So we do 0 minus 2.8, which is our expected value, squared times the probability 0.02. Then we're going to do that for x1. So 1 minus 2.8 squared times 0.10. Then for x equals 2, 2 minus 2.8 squared times 0.20. Then for x equals 3, 3 minus 2.8 squared times 0.42. And then lastly, for when x is equal to 4, that is 4 minus 2.8 squared times 0.26. Okay, and you would type all that into Desmos. And trust me, it equals 1. Okay? Which means in order to just find standard deviation, we need to take the square root of 1, which is 1. So that is our find part. We found the standard deviation. The standard deviation for the Northwestern example is 1. Then we have to interpret this. So the interpretation for every single standard deviation problem is always going to look like this. We would expect the typical deviation from the expected value to be 1 or 1 letter grade. Okay, so everything I'm about to highlight is what you would always write. We would expect the typical deviation from the expected value to be. You're always going to write that word for word. The rest of it's going to be based off the context of the problem. So this is saying that we would expect the value to deviate by 1 or 1 letter grade, which means even though our expected value was between C and B, that doesn't mean that those are the only values a student can get. They could get an A, okay, or they could get a D. We would expect them to deviate 1 letter grade. Okay? Does that mean there is 0 possibility to get an F? No, it's just not typical, right? Based off the data that we just collected and went through. Okay, any questions so far? And then the very last thing we're going to talk about in these notes is continuous random variables. Okay, this is where if you are taking calculus, or if you've already taken calculus, where statistics starts to tie into it. Okay, that doesn't mean we're going to do calculus in this course. It just means if you're taking calculus, you're going to start seeing some comparison to the concepts. Okay. So it says a continuous random variable takes on all possible values in an interval of numbers. The probability distribution of x is described by a density curve. So we have the normal curve and the density curve. Okay. When you think of discrete and continuous, think of discrete and continuous functions from Algebra 2. Okay. Remember, a discrete function is a function of points. It just has points on a graph, and you just list the points out. Makes sense because we said discrete means we can count all of our values. Versus continuous, continuous is going to be some sort of function. Okay, any type of function where you can put your pen in the beginning and draw the entire function without lifting up your pen. That is a continuous function. Okay, so if we're talking about a discrete function, it makes sense that a discrete variable takes on 1 value because those are our counting values. X is equal to 1, x is equal to 2, etc. Versus a continuous random variable can take on an interval of values because we could technically have x is equal to 1.1, 1.2, 1.3, etc. The probability of any event is the area under the curve. So I would highlight that. The probability of any event is the area under the density curve, and above, below, or between the values of x that defines that event. So if the area under the density curve is the same as the probability of an event, then the area under the density curve should always equal what? What should probability always equal? 1. And we just said probability is the area under the density curve, so the area under the density curve should also always equal 1. The probability is on the y-axis of the distribution. So finding the area equates to finding the probability of getting an interval of numbers. Okay. The probability at an event, for example, P of x equals 2 is 0 for a continuous random variable because the area under a point is 0. This is where it starts tying to calculus, right? If you're in my calculus class, when we get to integration, integration is the area under the density curve. Okay? So when we start talking about this area here, it's saying that if we had the probability of one event, that's the same as saying, okay, here's a graph with 1 point on it. Can I find the area under one single point? No, that's why it's 0 for continuous functions. The mean and the standard deviation of a continuous function are found using integration. Okay? You will not need to do integration in this course. That is what Desmos is for. But if you decide to take another stats course in college, that is where it's going to be, I would say, not imperative, but important that you maybe take a calculus course with it. Then we have continuous random variables are usually represented as functions. The continuous random variable that we will explore is the normal distribution, and we will come back to that at the end. Okay. It says, why do we have random variables? It says this is an important question to keep in mind as we continue to look at different random variables. We need random variables because they can represent more things that a single measurement cannot. One variable statistics, so everything we've done prior, okay, one variable statistics can only give us one type of measurement. Random variables are important because they help us apply it to theory and application problems. Okay, which means if you plan on being, let's say, a statistician or a data analysis or anything along those lines in college or your future career, random variables are important in order to be able to apply to all real life scenarios.